last time when we start to talk about the node voltage, we talked about what would happen if we have a voltage source in our, what do I say? If we have in our circuit, if we have the voltage source, how we are going to deal with that. And the problem with the voltage source was that when we were writing the equation, basically because we didn't know how much is the resistance in the voltage source, we couldn't write the node voltage equation, or in other words, the resistance in, we could write one equation, but at the same time that we get one another unknown, which was the resistance in the, for example, the battery. So it didn't help us. So to prevent, to work with that, we talk about the supernode and how we can use the supernode concept to basically get the result if we have the voltage sources in the system. Today, now we are going to look at the sources, but this time the last one or whatever we had so far was the independent sources. If we had the current sources, it was independent. We have the battery sources, it was independent. Now I want to look at what if we have a dependent source in the system, how we are gonna handle that. So let's see. So node voltage method. With dependent sources. Let's look at an example, so how we can handle that. So assume we have a circuit that has a current source. It's going to be Ix here. Sorry, it's Is. Goes here, and then we have R1. Then this here. Then we have another resistor here. It's going to be R3. And another resistance here. It's going to be R4. It's going to be R2. And then at the very top, we're going to have dependent current source. It's going to be 2Ix if this is going to be the Ix. So assume that we have the circuit like that has 4 resistance and it has 2 sources. One of the sources here is the independent sources. So it's always it's always the current it push into this wire or into the system is going to be Is. But we have here a dependent current sources, which the current is going to push into the system. It directly depend on the current is going to be at this resistance here. So this one affect directly the amount of current this one is going to put into the system. So if you have something like that, how we are going to work with that. So if you're working with node voltage method, remember the very first thing that we have to do, choose the uh, reference node. So if I go ahead and say, okay, my node is going to be one here, I have another node here, I have another node here, I have another node here. As I said, most of the time we get the node at the very bottom as a reference node. So assume I come here and said, this is my reference node. So basically, if I call them V1, so if I call them V1, V2, V3, and it's going to be at 0.4. So I call the 0.4 to be the reference point. In other words, we consider this negative, the all other is positive, and we calculate everything respect to node 4. I calculate all the voltage respect to node 4, assuming the voltage at node 4 is 0. So when we deal with this kind of problem, that we have the current source, which is going to be dependent, the very first step to do is just assume it is not the dependent source, just assume it is like the other sources, and start to write the equation. So the very first step, just do whatever we do so far. Assume it is not dependent, assume it's just a simple current sources like this one, and write the equations, write the node voltage equation. So if I want to start write the equation, as I said, I would assume that I am gonna have the current at each node leaving that node. So that's the very first thing I'm gonna assume. So I'm gonna assume here I have I going from 1 to 2. Here I have an I going from 1 toward 4. And then I have an I here going from 1 toward 3. The same for the second node that it is here. I have an I assume going from 2 toward 1. I have an I goes from 2 toward 4. And I have an I goes from 2 toward 3. And the same here. Then I have an I goes from 3 toward 2. I have an I goes up from 3 toward 1 from this, and I goes from 3 toward 4. So these are the I have. And then I start to write the KCL at each node. So the KCL at node 1, it means that the I goes from 1 to 2 plus I goes from 1 to 3 plus I goes from 1 to 4 should be 0. And then if I replace each I with basically the Ohm law, I'm going to get my equation. So I go from V1 to V2. So it's going to be the difference between voltage and then the resistor at the middle of them, which is going to be R1. And then for the second one, I go from 1 to 3. You'll see that I go from 1 to 3. Already in that wire, we have the current source. So we know the current in that wire is going to be 2Ix. We don't know how much is the Ix, but we know the current is going to be 2Ix and going from the right to left. So the current in this wire is always 2Ix, and it is in opposite direction of what we assume for I13. So it's going to be, for the I13 is going to be negative 2Ix. So instead of having I13, I'm going to put 2Ix, and it's negative because it goes in the opposite direction of I3. And then for the I goes from 1 to 4, have the V1 minus 0. And I'm sorry. Again, the same here for the one that goes from I to 4. We have the current source that is push the current in that wire, and we know the current in that wire is going to be Is. And then again, it push the current from bottom to top, and our current is, the direction of current we chose here is from the top to bottom. So the direction of what we chose is opposite of what is the current is here, so it's going to be negative, and the magnitude of that is going to be Is equal to 0. So it's going to be the first equation we are going to have for the KCL at the node 1. And then the same we can go for the KCL at the node 2. So at node 2, again, we have the I goes from 2 toward 1 plus I goes from 2 towards 3 plus I goes from node 2 toward 4. And if you add all of them together, it should come 0. So the first one goes 2 to 1 is going to be the difference in the voltage divided by the resistance between them. Then 2 toward 3. 2 toward 3 is going to be again V2 minus V3. So it's the voltage difference. And then we have the R3. That's going to be plus here. And then plus goes from 2 toward 4. So it's going to be V2 minus 0. 0 here. And then we have the R2 here is 0. And then we have the KCL at 3. So at 3 the same. We have the I goes from 3 toward 1 plus I goes from 3 toward 2 plus I goes from 3 toward 4 is 0. And then, so 3 to 1, if you look at that 3 to 1 is that we know that the current is still, we don't know the Ix, but whatever the Ix going to be, the current in that wire is going to be 2Ix. And the direction of the Ix is going to be from the left, from the right to left. And then it's going to be the same as the direction we chose here for the I31. So it's going to be, instead of I31, I would put 2Ix. And it's positive because both are in the same direction. Then 3 to 2 is going to be V3 minus V2. And the resistance between them is R3. And then we have for the, this one is going to be V3 minus 0. The current goes from 3 to 4. So voltage at 3 minus the voltage at source. And then we have the R4 is 0. So we have 4 nodes in this system. We chose one of them to be the reference, and then we have 3 other nodes. And so we write the equation for 3 other nodes. Assuming that we know the Is, we have V1, V2, V3, and Ix. So we have 3 equations here, but we have 4 unknowns. We have 3 equations, 4 unknowns, V1, V2, V3, and also Ix is unknown. So how we are gonna deal with that? Whenever we have something like that, we have to go ahead and try to figure out another equation, somehow find another equation to help us to solve the problem. And for example, here, if I want to look at that, if I go look at this setup here, so it's going to be equation 1, 2, and 3. I need another equation. Another equation, if I look at this circuit, look at this one here, the one that I have here. If I grab this part and bring it out, so it's going to have I have the V2, then I have the resistance, and then I have V1. So I have a V2, V3, and I know that's the Ix. I know, again, I don't know how much is Ix, but I know the current is the Ix in that R3 that I have it here. Now look at this. If I want to write the Ohm law for this single resistor, regardless of, just disregard the rest of the, I will just circle. Just look at this one. I want to write a Ohm law for this one. The Ohm law is that the delta V, the difference, basically the Ohm law, what the Ohm law would say is that the voltage at R3, so whatever is the voltage at R3 is equal to I times the resistance, and the voltage at R3 is the difference of the voltage at both end of the resistor. So the voltage at R3 is just delta V is V3 minus V2. So this is the difference. The voltage at R3 is the difference, is the voltage difference between two ends of that resistance. And because the I goes from V3 toward V2, remember that we always says that the I goes from the positive to negative in the resistor. If we have this condition, we know that it should be like that. If it goes from positive to negative, so the V3 should be larger than V2. Otherwise, the I doesn't go from V3 to V2. In order that I goes from V3 to V2, the V3 should be larger than V2. So the delta V, or the difference of the voltage at two ends of the resistor, which is going to be equal to the resistance voltage, is V3, and it's going to be IXR3. So if I go ahead and then I find the IX as a result, it's going to be V3 minus V2 divided by R3. So this is going to be the IX, and it's going to be my fourth equation. Now I'm going to write the rest here on top here. So now if I go here and substitute this one, the IX, in these equations, then I'm going to have the equation 1 is going to becomes V1 minus V2 divided by R1, then minus 2IX, and the IX is V3 minus V2 divided by R3. We have it from here, and then we have negative IS minus IS is 0. The equation 2 is going to give us, the second equation is going to stay exactly the same as it is, divided by R1 plus V2 minus V3 divided by R3 plus V2 minus 0 divided by R2. And then the third equation is going to give us 2IX again. It's going to be 2, and we have the IX here, V3 minus V2 divided by R3 plus V3 minus V2 divided by R3 plus V3 minus 0 divided by R4, going to be 0. Then here we have the three equations, three unknown, and you know the IS is known. The R1, R2, R3, R4 are known. So the all the unknown are here are V1, V2, and V3. And then if we had the value for R1, R2, R3, and R4 and IS, we could just simply substitute those values and find V1, V2, and V3. And eventually, if we needed, we could go back and find all these current in the system if we needed. Okay. Now let's look at another example, see how we do the calculation for if you have the dependent source in the system. As I said, when we are working with the node voltage, if we have the current source, either dependent or independent, is relatively more straightforward to work with compared to the time that we have the voltage source in the system. And the reason is that um, we don't know the resistance of the voltage source. For example, if you have a battery in the system, we don't know what's the resistance of that battery, and because of that, it's not gonna be that easy to write um, it's not that going to be easy to write a node voltage. And remember, I said there are two ways of working with that. Either one of them is that either get the reference at one end of the battery or voltage source, and then the voltage at the other end is going to be equal to the battery. So it's the easiest way, if it is possible, to do that. So the first, the easiest way to get around that is, if it's possible, get the reference node at one end of the battery, and then the voltage at the other end of the battery is going to be equal to the battery. If it is connected to the positive side of the battery, it's going to be positive. It's going to be, if it's connected to the negative side of battery, it's going to be negative. But sometimes it's not possible. Sometimes it's not going to be possible to get the reference node at one end of the battery or the voltage source. And if it's not, that's how we are going to use the super node to solve the problem. Not it's going to be the same if we have the dependent voltage source. So it's going to be very similar to the independent one. If we have the dependent source, again, it's the same story, because we don't know the voltage, because we don't know the resistance in the dependent voltage source. We have to somehow find a way to get around that. So let's look at an example. Assume there is a there's a resistance at the very top, then we have comes here. It's a voltage source. Then we have and there's a vertical resistance here. Comes here. It comes, there's a current source. Current source comes on here, and then we have another resistor here. Like that. So it's going to be positive on this side, negative on this side. It's going to be 0.5 Vx. Then we have here Is, and then we have R1 here, R2 here, R3 here, and then the R4 here. And then we know that's going to be the negative, is going to be positive, and the voltage in R1 is going to be Vx. No, I can put it off. So it's R1, and the voltage here is going to be Vx. So here, the voltage is Vx. So assume this is what we are given and we want to solve this problem. Again, remember it's given in parametric, but uh, uh, R1, R2, R3, and R4 are known. Also ISR is known. So we know all the resistance. Basically, we know R1, R2, R3, R4, and IS. These are known. And then we want to solve this circle. So the Vx is not known. And as you see here, we have two sources here. In the previous example, the sources we had, both of them were current sources. Here we have one current source, which is known what it is doing. And then we have the dependent voltage source, which the voltage is going to keep in the system is function of the voltage at this resistance here. So whatever the voltage is that in that resistance, the voltage in this battery is going to be half of it. So now we want to solve this problem. The one thing is that the first thing we're going to do is to find our nodes and then the reference node. So we have this node here, we have one node here, we have one node here, and we have one node here. And then we want to find our reference node. Again, probably the easiest one is to keep this node at here, the node 4, I'm going to call it, as a reference node. And then I'm going to say, okay, this one is going to be the V1, the one in the center is going to be V2, and this one is here is going to V3. So that's how we have them. So we are going to put the reference here. So that's our reference. The V4 is our reference node, and then we have V1, V2, and V3, and then we want to solve this problem. Similar to what we had before, with the previous example, the very first step we are going to do is just start to write the all the KCL we can write for the nodes. Now, if I want to write that, the problem is that, again, if I see here, if I have the current goes up here, is I goes from 1 to 3, then I have the current goes here from I goes from 1 to 2, and then I have the current goes here, I is going 1 to 4. Same here, I have the I goes from 2 to 1, then I have the I here goes from 2 to 4, and then I have the I goes from 2 to 3. Same here, I have the I goes from 3 to 2, I goes from 3 to 1, and I goes from 3 to 4. Now, if I want to start to write a KCL at the V1, well, the 4 is the reference, so I cannot write anything at that. If I want to start to write it for the V1, is that I have to write it. If I want to write a KCL at 1, the problem is that what I'm gonna get is gonna be I1 3 plus, I'm sorry, I1 2 plus I1 3 plus I1 4 is 0. And if I write it again, it's gonna, for the very first one, is gonna give us V1 minus V2, and then divided by what? We don't know the resistance here. So it's the V1 minus V2. We don't know the resistance here. So although I can write it furthermore, but it's not going to give me anything useful because I don't know that value here. We don't know the resistance value in the battery. So basically I cannot use I cannot use this equation. The same if I write it for the V2, if I write the KCL at 2, again it's going to be I21 plus I23 plus I2 toward 4 is 0. And then I21, again, I'm going to get the V2 minus V1. And then I don't know the resistance here. Again, it's not going to give me anything helpful because I don't know the resistance. I don't know that term. So it doesn't matter what about the rest of the these two. If I write it down, I'm not going to get anything out of that because I don't know that value in that battery. To prevent that, so I can't write anything at 1, I can't write anything at 2. So to get around that, to prevent that, that's how you have to get the have the supernode. So I have to define a supernode that basically wrap these two, V1 and V2, or in other words, the wrap around the battery. So I don't need to deal with the battery. So if I'm going to get the supernode, assume I'm going to get the supernode like that. So so this is my supernode. So if I get the supernode, or basically the region, then instead of writing for the 1 or for the 2, I can write the KCL at supernode. In other words, I select a region in the circuit. Everything enters that region should leave that region, or everything enters that supernode should leave that supernode. So if I write that, I'm going to have here I have I13 leaving, then I have I14 leaving, then here I have I23 leaving, and here I have I24 leaving, and this is going to be 0. And then I can write the equation for this one. So I1 toward 3 is going to be V1 minus V3 divided by R1, plus I goes from 1 to 4 is going to be V1 minus 0 divided by R2. Then the one I goes from 2 to 3 is going to be V2 minus V3 divided by R3. Then plus the one goes from 2 to 4 is going to be V2 minus 0. Oh, sorry. So this one, also the one goes from 2 to 4. We already know the magnitude because we have the source in the current source. The current source is IS and it goes from bottom to top. What we chose is in the opposite direction. So it's going to be negative IS here. That's going to be 0. So this is the equation we get from the supernode. So basically we use V1 and V2 and V4 already. V4 is a reference and we use the V1 and V2 at the supernode. So the only node left is the node 3. So I can write the KCL at 3. And then it tells me the I goes from 3 to 1 plus I goes from 3 to 2 plus I goes from 3 to 4 should become 0. So for the one goes from 3 to 1, it comes up V3 minus V1 divided by R1. Then we have the one goes from 3 to 2, it's going to be V3 minus V2. V3 minus V2 divided by R3. And the one goes from 3 to 4 is going to be V3 minus 0 divided by R4, and it's going to be 0. So now I have equation 1 here, and I have equation 2 here. The problem is that I have 3 unknown. There's a V1, there's a V2, and there's a V3 here. So there are three unknown in this equation that I have here. So somehow I have to find another equation to help me, because I have two equations, three unknown. So I'm going to write the rest up here. Assume I'm going to just grab these things and bring it out. So if I put here, so it's going to be V1, and then I have the sources, and I have V2. So it's a V1, it's going to be V2, it's going to be plus, it's going to be minus, it's going to be 0.5 Vx. So if I have this equation, I want to write the equation for this one. I go from the negative to positive. So it's going to be V2 plus 0.5 Vx is V1, or otherwise it tells me the V1 minus, because we go from positive to negative, 0.5 Vx. It's going to be V2. So always when we have a battery in the system, if it goes from negative to positive, it adds it. So if I go from V2 plus 0.5 Vx, it's going to be equal to V1. Or if I go the other way, if I go from the positive to negative, it's going to be V1 minus that battery, because I go from positive to negative. It gives me this. Let's write it the other way, so maybe it's easier for you to remember. So it's always like that, where it goes from the negative to positive, it adds to whatever you have. So I have the V2, then it goes from negative to positive, it's going to be plus 0.5 Vx, it's going to be V1. So this is the same equation I wrote it. So I just, the Pearson, I write it V1 minus that. So this is one equation. So it gives me the third equation. But then the problem is that it also adds another unknown. So I have the third equation, but now I have four unknowns. I have V1, V2, V3, and then the Vx is unknown. It's not going to help me. So I have to get again another equation somehow to bring down my unknown or increase my number of equations. So the next thing that I may write is that I look at this R1 here. So if I draw that, it's going to be look something like that. Is a R1, so Vx, it's a negative, so positive, and then it's going to be V1 at this end, it's going to be V3 at the other end. Now, if I write the Ohm law for this equation, if I want to say I would write the Ohm law for this one, you look at that. I know that because it's a positive, it's negative. The reference, the voltage in that resistance is going to be delta V. The difference between two ends of that resistance, and because it's positive at this time, as negative at this time, I know that the current should actually go from V3 to V1. Basically, V3 should be larger than the V1. So the delta V is the V3 minus V1. So the voltage in the resistance is the difference of the voltage at two ends of that. Also, I know that the voltage is going to be Vx. At the same time, I know that the voltage in that resistance is Vx, and that Vx is the same here. So I can just put it here as a Vx. And that I know, because Vx is the voltage at the resistance, and the voltage at the resistance I know is the difference between the two ends of that. So the voltage at resistance is the difference between V3 and V1, and because the V3 side is positive, the V1 is negative, so I know the voltage should goes from V3 to V1, the current, because it always goes from positive to negative. So the V3 is larger than the V1. So the difference between the two sides of the resistance is V3 minus V1. And we know that difference at the two end of the resistance is equal to the resistant voltage. So it's going to be equal to Vx. And it's going to be our force equation. So now if you look at here, we have four equations and we have four unknowns. And eventually, if we start to substitute them together, we can, I would say, we can go ahead and solve this problem. In other words, if I, for example, here, if I substitute the Vx here with this magnitude, V3 minus V1, then I have the third equation, which here is only has a V1 or V2 or V3 in that. So 3 and 4, if I put the 3 and 4 together, I substitute Vx with that. So it's going to be V2 plus 0.5, and then I substitute Vx with V3 minus V1. It's going to be V1. That's going to be the fifth equation. So basically, I can solve 1, 2, and 5. If I solve 1, 2, and 5, it's going to gives me V1, V2, and V3. Because the only unknown is 1, 2, and 5 are V1, V2, and V3. Remember when I was talking with the resistance, but I wrote one note and I said, make sure that you remember that note, is that if we have the resistance, the current in the resistance is always goes from positive to negative. And the current always goes from the higher voltage to the lower voltage. So if I have, for example, VA here, and I have the VB here, to force the current go from A to B, VA should be larger than VB. Otherwise, the current goes from B to toward A. So if I want to force the current goes from A to B, always the A should be larger than B. And then I know the V, if this is the VR, the VR is always the voltage of difference of two ends. So the VR is going to be the larger value, which is going to be VA, minus the smaller value, which is going to be V. Always in the resistance, it goes from positive to negative. In the battery, it may goes from positive to negative or from negative to positive. If it goes from negative to positive, it means the battery provides the energy into the system. If it goes from positive to negative, it will recharge the battery. But for the resistance, it always goes from positive to negative. So if you know the direction of the eye, this is going to be the direction, this is going to be the polarity. If you know the polarity, this is going to be the direction. It is going to be always like that. So let's look at another example, and this is going to be the last example we are going to look at in the node voltage analysis. And after that, we moved on to other methods. So we are I'm gonna have the circuit like that. Then we have the battery here. And the volt. Let me clean that. And then we have 150. We have the resistance here. and then we have another resistance here, and then we have another resistance here, then we have another resistance also here, then it goes here, and then we have another source here, and then goes there. It's going to be negative and positive. That's going to be 10 ix. That's going to be 2 ohm. That's going to be 1. It's going to be 3 ohm. It's going to be 10. It's going to be 15, 20, and 10. So I didn't write the ohm. They are all in ohms. So this is going to be point A, B, C, that's a D, E, and try to have it lower. It's a D, and it's going to be E here. That's going to be F at this point. That's going to be G to the very top. So these are the. So assume this is what we have and what we want to analyze this system. So again, this time the same as the first. We have the battery in the system. Second, we have the dependent source in the system, or this dependent battery. And remember, when we have the battery, usually as I said, there are two ways that we handle that. First, we are going to put the reference node at one end of the battery, and the voltage at the other end is going to be known, and it's going to be equal to the battery. If it's connected to positive side of the battery, it's going to be positive. If it's going to be connected to negative side of the battery, it's going to be negative. Otherwise, if we cannot put the node at this one end of the battery at the source, at the reference, if we cannot put the one end of the battery at the reference, we have to use the super node. So this is all these two ways that we can handle the battery. Either we have to use the super node, or either put the reference at one end of the battery to work with that. So if I have something like that, and now I have numbers, how I'm going to work with that. And let me see, where's the it's the ix. Let me, it's confusing, make it small. So if this is 10 ix, make it lowercase, 10 ix, and assuming the current in this one is ix. So this is the, I would say, this is the dependent source, and the value of that depends on this current in this wire here, or this resistance here. So the very first thing that we need to know, so these are our nodes here. So we have the nodes here, we have the node here, we have the node here. So these are our main node that we have, and then we want to find a reference node in our system. So which one is going to be the reference node? Again, because I have a battery in the system, I said one way to handle the battery is to put the reference node at one end of the battery, and then the other end of the battery, the voltage at the other end of the battery is going to be equal to that node. So to do that here, if I want to do that, among all the nodes I have, to handle this battery, so I don't need to be worried about this battery, I'm going to put the reference node here. So assume this is going to be my reference node. in this point. I'll put it the other ways probably. So I make this reference node. So it means that the voltage in that is going to be 0 respect to the voltage at all the other nodes. By doing that, the one end of the battery, I set the one end of the battery is 0. The other end of the battery, the voltage at the other end of the battery is going to be equal to the battery because it's connected to the positive side. So I already know that the VF is going to be equal to 20. And because it's connected to positive side, it's going to be positive 20. Because one end of the battery is connected to the reference, the other end is going to be the voltage at the other end is equal to the voltage of battery, and because it's connected to positive, it's going to be positive. If it was connected to the other side, it would be negative 20. So by doing that, I know the voltage at C and I know the voltage at F. So the voltage at two nodes I already know, but there are other points that I have to find the voltage at them, and then it's going to be the V at this point at the B. So I have the V at the B, and then I have the V at the D that I have to know. Then I have the voltage at the E here that I have to work with them. Now to start to write the I would say the KCL or the node voltage method. So I start to assume the voltage leaving the current. So I start from the B. So if I have the current goes from here, here, and here. So the I goes from B toward C. The I goes from B toward D. And the I here is I goes from all the way up there. It goes from B toward A, G, and then eventually toward the F. That if I want to say that. So this is what I want to do. Now look at here. If I want to write it goes to it goes from B to F. I have 1, 2, 3 resistance on my way. So it's not like previous one that I write simply. I would go ahead and say previously if I want to write it, I would say V B minus VF divided by R that is between B and F. Now there is not one resistance, but rather there are 3 resistance from here to here. What I'm going to do with that? Because there's not one. To solve that problem, I'm going to replace, look at these 3. One resistance, then the next one goes right after that. Then another one goes next right after that. Look at these 3. These 3, the 1, 2, and 3, these 3 are in parallel, are in series, because the one of them goes right after another one. So I can replace that. I say, okay, this gonna be look like this. So if this is try to write very quickly. So this is a point B, and then I have 10 here. It's a point C, and then I have negative positive here, and it's going to be point F. It's going to be 15 here. It's going to be that one here. And then I have this here, this here, and this one. So if it's this one at this top, now it's going to be the equivalent resistance, because I have 3 resistance in series, And then the equivalent resistance with these three one is the, just add them together. Because these are in series, it's going to be 1 plus 2 plus 3. So 1 plus 2 plus 3. So it's going to be 6 ohm. So I replace these three with one resistance. And then I have the 15 here. I have a 20 here. Oh, here also I have, let me see. Forgot I have 10 here. Oops. So it's a 10 also here. And how much? So also I have a 10 here. So these are the one we have. So here again, I will write that. So I have the VB here, and I have the, I would put the reference here. At this point, also I have the VF that I know it's going to be 20 here. Also I have the VD here and VE here. Now if I get rid of these, for this one, again, I'm going to write the KCL here. So it's going to be the V go from B to D. Sorry, so I goes from B toward D. So I goes from B toward C. And so I goes from B toward F that we have. This is the C. And then if I write the KCL at B, what I'm going to get is that the sigma I should come 0. Therefore, let me write it the other way, it's easier. So it's going to IBC plus IB D plus IBF should be 0. Therefore, I goes from BC is going to be VB minus 0. And then there's a 10 ohm here. Plus I goes from B toward F is going to be VB. And the VF I know is 20. And minus VB. So it's going to be, this is the VF. So it's a VB minus VF. I just write it, you know. And the resistance between them is 6. And the one goes down here is going to be, write it with another color. So this is the VF. And then for the goes from B toward, so this is the BC, this is the BF, and then BD. So the BD is the one goes from VB minus V at D and divided by 15 is 0. So let me change that so you don't get confused later on. So this one is there. I said here is a BF, so it's a BF. And this one is BD. I rewrite them to make sure the order of these three is the same as order of these three. So it's a BC, BF, and then BD. So it's the first equation I would get if I write it for the B here. Then also here, let me change, that's the BF, not the IBF, is the BF. So this is what we get from this node. So we use this node. The C, we use it as a reference. The F, we already know that. And there's so many unknown, and we use these three nodes. The only nodes left is this one and this one that we want to use it. And then the problem is that these two are connected to the battery. So even if I write it, if I want to write the KCL at this node, because it's connected to the battery, it's not going to give me anything because I don't know the resistance, the battery. So to do that, one thing I have to do is, again, either like here, we put a reference at one end of the battery, which we already do that. So we already put the reference at one end of the battery. The other option is that I have to take these as the, I would say, the super node. So I have to go ahead and assume this is the super node here, because I cannot write anything for the node D. I cannot write anything for node E because both of them connected to the this battery, and we don't know the resistance. So we have to get the super node. So if I go ahead and assume this is the super node here. So I would consider that as a super node, and then I will look at what current enters or leaves that super node. And I said in the node voltage, we always assume the current leaving. So I have to look at the current leave that and should use the current. So it's going to be the current goes from D toward B, then the current goes from D toward C, and then the current goes from E toward F. And I said this current also, we know that current in this one from here, we know is IX. And then if I write the KCL at super node, then I have the current goes from D toward B, plus the current goes from D toward C, plus the current goes from E toward F, should comes as 0. And then I can go ahead and write this equation here. So it's going to be VD minus V for the first one, B, divided by 15. Then D towards C is going to be VD minus, we can use the IX, but I'm going to write it like that. But also we know the current already is negative IX with that wire as well. But the IX itself is unknown. Remember that. So VD minus 0, so D minus 0 divided by 20. And then the one goes from E toward F is going to be VE minus VF, which is, we know, is 20. So it's the, again, it's the VF, and we know it is 20. And then divide that by 10, it's going to be 0. So now I have two equations. I have equation 1, I have equation 2, and then I have VB is unknown, VD is unknown, V is unknown. So I have 2 equations and I have 3 unknown still here. Now that I have 2 equations, I have 2 equations and 3 unknown, so I have to go ahead and try to figure out some other equation in the system to use. So I already use all the nodes I have for the node voltage method. So I use the node B, I use the node C as a reference. I use the node F and I know the voltage there, and I use the node D and E as a part of the super node. There's no node left that I can write the KCL at those nodes. So I don't have any node left. So I have to go and keep looking here to see what I can find to use. Again, one other thing I can to use is that I can go and look at this. If I bring this out, if I bring that, it's negative, it's positive. So it's going to be VD, and it's going to be, so it's going to be VD, and it's going to be VE at the other end, and I know that this is going to be 10IX. Now for that one, again, I know that if I go from the negative to positive sign, I can say right that the VD plus the voltage here, and how much the voltage here is 10IX plus 10IX. Oops. Is V equal to VE, because I go from the negative to positive. So the VD going from negative to positive, so I'm going to add the voltage of the battery, and then I have the VE. It's going to be VE. So it gives me one more equation. It's going to be the third equation. But the problem is that it gives me one more unknown. So now I have the IX also involved in my equation. So here I have VB and VD and VE unknown. Now I add another equation and I add another unknown. So again, it's not going to help. I have to find add another equation to get the number of equation and number of unknown equal. Now, if I come here and look at it, I can't write anything for example, this resistance. I cannot write anything for this resistance, nor for this one, either for this one. But in this one, I can write because I know the value in that one is going to be IX. I can write one equation here. So if I draw that, this one, so if I draw, goes from, so if I draw this C to D, it's going to be C, then it's going to be resistant, then it's going to be D. And know that it's going to be the VC, which is 0. So let me put the so that is the reference, and we know it says VC and it's going to be 0, so it's going to be C, and it's going to be VD, and I know that's going to be the IX in that direction. If this is the IX going from C toward D, for sure I know that is going to be positive here, it's going to be negative here, because it's going from the positive to negative in the resistor. When we have the resistance, it always goes from the positive to negative. I know the direction, so it should be positive to or negative. Now, if I write the Ohm law, I know that the voltage at here, so this is the 20 ohm. And if I know the voltage here, the voltage at this 20 ohm is the voltage is the difference of the voltage at two ends of that. So we know that the I goes from the C toward D. I goes from C toward D, and the delta V at the resistance is the difference between the voltage at two ends. And because the I goes from C toward D, the voltage at C should be larger than the voltage at D. So the delta V is the VC minus VD. Because it goes from the C toward D, the voltage at C should be larger than the voltage at D. And it's going to be VC minus VD. And we already know the VC is 0. So the delta V is going to be negative VD. whatever it is going to be negative VD, because the VC is 0. And we know the VC, because the I goes from C toward D, the VC should be larger than the VD, so that's the delta V. And then we know that the Ohm law is gonna tells us delta V is gonna be the IX and then the R, which is gonna be 20. So therefore, if I substitute that, the negative VD is gonna be is gonna be 20 IX. IX, or in other words, VD is negative 20 IX. And this is gonna be my fourth equation. So I have one equation here, the second equation here, the third equation here, and the fourth equation here. And then if I substitute VD here, I substitute the IX with the VD here. From this equation, if I substitute the IX at the 3, then I have the equation that all is as a V. So then I have 1, 2, and 3 to do that. So in other words, to continue that, I will substitute IX in 3 from 4, and then solve 1, 3 to get the VB, VD, and VE. So find the IX from here, substitute it in the third equation here, then it's going to be as a function of VD and VE. Then you have the 3 equations, 1, 2, and 3. All of them is the unknown is, it has 3 equations, 3 unknown. It's going to be VB, VD, and VE, and then you solve them. And then you can find the value of VD, VE.